Okay, thank you, Eric. This is my first talk to human being in the same room since a couple of years, so I wish to thank you again, the Institute and the organizer of the program and of the conference for bringing us together. It was really due time. I was looking for it, and I realized the audience is quite diverse, so before even starting, I would like to put a little things into context very quickly. And so if this was a landscape of methods to compute the boundary, to resolve the dynamics of a boundary to body problem in the air, a while ago, I would say, but now that landscape looks like this, that is certainly a signal of interest, of course, and it couldn't be otherwise in the gravitational waves era, but I still find, even accounting for that, quite extraordinary development that the field has been going through in the last decade or so. And the red thing is that my tribe lives in, so we live in the post-Newtonian territory, and we apply FT methods to study the dynamics. So I will not go over all of these, but I think everybody can recognize some of their own stuff, and some of these elements will come through the rest of my talk. So, coming back to the title, I will talk about radiative contribution to conservative binary dynamics, more specifically to processes where a real gravitational wave is emitted by the system and then scattered and reabsorbed by the system. That is a process where energy is conserved, and it is contribution to the energy of the system, and you must account for that to have precise waveforms. As a further motivation, I will tell you that in this moment, 4pm is history. There are different groups who have done it mutually consistent way, so this is achieved. The 5pm, we are almost there, and there are basically two almost complete derivations of the dynamics. The first one is tutti frutti, the so-called tutti frutti method by Geneva, where many of the methods which I presented in the previous chart have been combined together in an efficient way, and they produced a 5pm Hamiltonian, which is almost complete in the sense that there are just two unknown coefficients in this Hamiltonian. And they even went further and had a 6pm Hamiltonian modulo 4 new coefficients for a total of 6 for the dynamics up to 6pm. So this is the first almost complete derivation of 5pm dynamics. The second comes from my tribe, and basically from the contribution of two groups. There is me and Ricardo who computed these relative contributions, which I'm talking about today. There is a group of Blumlein who computed the many graphs contributing to the purely potential modes. And there are cross-checks. Again, me and collaborators computed a subset of these diagrams, and we have found the perfect match. And they computed also later on relative contributions, finding a mismatch, which is related to this memory contribution, which will be the subject of my attention in the later part of the talk. Also, let me add that the amplitude people have computed, have reached 4pm precision, which overlaps with these two Hamiltonians and Lagrangians, and there is also perfect match. So the situation is almost, this word, satisfactory. And so we have one almost complete derivation, two mutually almost consistent derivations. And if we try to put them together and see if they agree, you will not be surprised to find that there is a disagreement. This is another work that Biniramoor and Geralico made. They looked at the scattering angle. So the dynamics we have computed has been computed for the boundary problem, but once you have Hamiltonian, you apply to anything. So you apply it to the scattering problem, and you can expand the scattering angle in inverse powers of the angular momentum, or the impact parameter if you want. And then each of these objects you can expand it in terms of the symmetric mass ratio, mu, which has nice analyticity property, which I'm not investigating further here. So at 5 p.m., the relevant terms are these ones. I can do the expansion. At nu equal to 0, it is basically Schwarzschild, and everything is OK. In the first order, it is a so-called Selfforce limit. Again, the Hamiltonian of the Bineta-Murger-Alicorn and our Lagrangian, AFT Lagrangian, agree perfectly, and trouble starts at this point. There are 3 coefficients referring to the j powers of j, 4, 5, and 6. The 5 and 6 are not informative because on the tutti frutti side, this is where the 2 unknown coefficients are hidden. So we leave them apart, but this chi4 is complete on the tutti frutti side, and it has a mismatch with the FT Lagrangian, not surprisingly extracting in that piece where this memory is contributing. Well, we don't know for certain that it is that piece, but since there is already a disagreement in the FT, and there is also a mismatch here, so clearly there is something to understand here, and this will be the object of my attention. So from now on, so now this is end of the motivational part, if you need it. And now let's just start a little bit from the beginning. In the effective field theory, we are basically integrating the equation of motion for a gravitational field and plugging in to derive the dynamics of a binary, and we do it in following field theory methods. So in this graph, our convention is that the black line are the binary stars. They are considered as classical sources, non-dynamical, and the time flows, you may say, in that direction, but it doesn't matter really. And these colored lines are the gravitational interaction exchange by the 2 stars, and they can be very complicated. The essence of the FT is, or any in general of a post-Newtonian expansion, is the method of region. That is, every time you have a solution of the equation of motion for the gravitational field, that is in field theory method, in field theory language, a propagator, a Minkowskian propagator, well, our amplitude colleagues, they aim to solve these integrals using the full propagator. And they can do up to 4 pm, which is remarkable, but if you, in PN, which is the phenomenological relevant thing, it's just sufficient to cover the 3 pm, which is clearly not enough for even for LIGO. So in the post-Newtonian expansion, you just approximate this propagator in 2 ways, according to the regime where you are. In the near zone, so-called near zone, where the momenta are much larger than the frequency, you approximate this integral with this expression, and in the so-called far zone, in the opposite limit, you approximate it with this expression. So you just keep the propagator and expand exponentially. So the expansion gives rise to in the end, to the radiative multiples of the system, and that expansion do mu not to capture any physics which is around the pole, because the convergence radius of this expansion stops at the pole. So every time you have a real gravitational wave involved in your process, you know you're going to miss it. Okay, first of all, does this splitting make sense? Yes, because, for example, if you have an integral in which only one propagator is involved, so not this diagram, for example, you can see that you can split this integral of this correct quantity is equal to the integral of the 2 pieces plus some objects which are scaleless in dim reg, so they are 0. So even if the 2 expressions are very different, this is different from the sum of these, and indeed this is an infinite divergence, this is an ultra-rare divergence, but if you combine them together and you do the integral, you obtain the correct result. And this result can be extended to a situation where there are 3 propagators. This will be the correct, precise, exact result, and you can show that it is equal to the sum of the contribution when every propagator is taken in the near zone approximation, and another contribution where everything is in the far zone approximation. What happens to the mixed term? Well, when you have 2n and 1f, you have the diagram like this, and this is purely dissipative. Okay, so this does not contribute to the conservative dynamics. And the other limit, NFF, is forbidden by momentum conservation because you have two very low momenta, they cannot sum to give a very strong momentum. Okay, so this is the essence of the method of regions, and it has been applied unconsciously for decades. And so with this with knowledge, we can just go on and compute, show you how it works at 4 p.m., where everything is non-controversial. So pictorially, what I said before is the following. You have in the near zone where everything is in the N approximation, you have some diagrams which are intraviolet divergence. And in the far zone, you have this diagram, which is infrared, ultraviolet. So this is infrared divergent, and this is ultraviolet divergent. But if you combine them together, the final Lagrangian is finite. And since you have used the same regulator, dim-reg, into the two regions, the sum is entirely predictive, and you have this finite coefficient. So this goes away. This is an Moroccan term which is known since 88, Blanchet d'Amour. And this number is a prediction of a theory, which must plug in the energy of the binaries to get the correct result. So 4pn, everything is fine. And as we finish 4pn, we just thought, okay, let's do the same thing at 5pn. What are the new graphs which you need at 5pn? Well, this one is the one at 4pn. You just have to calculate it expanding the multiples. Here, before you adjust the mass, you just have a Newtonian energy because it's 1pn more. And for the quadrupole, rather than keeping the lowest order expression, you keep the 1pn corrected expression, which is known. So this is already done. Then you have to add the other multiples. So that is the mass octupole, the magnetic quadrupole on this side. And then you can enhance this by 1, and you will obtain the mass dipole, which is 0, because you're in the center of mass. And then the magnetic dipole, which is the angular momentum in this language. So we have this diagram. And the two diagrams which will give troubles, the so-called memory diagram and the double emission. And you will notice that the graphics is different the way I designed them, because these were the 5 diagrams which me and Ricardo computed first. We just didn't realize there was also this one. And Blumlein and collaborators pointed it out in the latest work. I have also divided these two contributions in powers of the symmetric variation in order to remind us of what I said about the scattering angle. So this diagram contributes to the first order in the scattering angle. So you already know the end of the story. That should be fine. And these diagrams contribute to the quadratic part of the scattering angle in the symmetric frustration. So this is where we have troubles. And in particular, I will not focus on this because it is basically the same kind of the other two, and really focus more on these. The reasons these are qualitatively different is that from these is that here you have a multiple which is conserved. The angular momentum is conserved, as is the energy of the system. So that cannot give the radiation. So these diagrams have only 2 radiative gravitons, and basically only 1 frequency, because frequency is conserved of a vertex. While here you have 2 independent frequencies, and also here. That's what makes the difference in the end. So let's start first quickly with these diagrams, which are the tails. I call tail every diagram which have a conserved multiple at least in it. And actually, we have computed much more than this. We are able to compute this kind of diagram for every kind of multiple. And this is the result. So this notation R is a collective index, how many indices you want. So mass octupole, hexadecapole, etc. We have the answer for everything, for every multiple here. Let me just drive you through let's read the solution. The free coefficient is basically nothing else than Thorne emission coefficient for the given multiple. It's just a property of these integrals, but the coefficient is the same as the emission coefficients. Then you have, okay, for example, R equals 0 is 3 derivatives each for the quadrupole, 4 derivatives each for the octupole, etc., etc. Yeah, we are in frequency domain. And the same structure, which is consisted of a pole, the ultraviolet pole I was mentioning about, a non-local term, which is also very well understood, and the finite piece, which is the prediction, which you have to plug in your Hamiltonian. And we have a general expression for this number for every multiple. And in particular, you recover the 41/30, which I showed you before, 4pm result. And the new number, which you need 5pm, which is this 82/35 for the mass octuple. Am I missing something? No. How much time do I have? Yes, I have some time to comment a bit about this. This expression of a magnetic multiple is slightly different from the one we had used in the first work, and the coefficient is also different. And let me clarify this a bit. This is our work of 19, where we used the three-dimensional expression for the magnetic quadrupole. And we have this. This is exactly equal to this expression where we use, of the paper of 21, where we use the d-dimensional expression for the magnetic quadrupole, which does not involve the Levi-Civita tensor. They are equal, but at the time, in 19, before this work, when this multiple didn't even exist, as you see from the date, then the counter group of Bloom length, they compute the near zone dynamic, they sum everything together, the divergence, the ultraviolet and infrared pole, they cancel, and they just check this number against the scattering angle and say it doesn't work. And Damour, Bigny, and Geralico confirm. But how counts that it doesn't work if the two quantities are equal? It counts because, these expressions are equal in the equal 3. And since the near plus far zone computation sum together, they are finite, I'm allowed to use them. But if I do this, I must use both definitions on the same side. And while in the far zone, it was at the time natural for us to use the Levi-Civita tensor, in the near zero calculation, there is nowhere for this Levi-Civita tensor to appear. So it is not natural for this kind of calculation to use it. So they were kind of summing apple and oranges here. And so that's why I think it didn't work. And so in retrospective, we should have thought about it and give a result directly in this multiple, which doesn't use the Levi-Civita tensor, because in that case, it's more easy to make the comparison. And so if you use this, then you can add this to the near-zero calculation, and you get the good result. And you check the scattering angle, and everything works. So from the tail point of view, I would say we now, after some trial and error, we have a good understanding of the situation. And now let's come on to where the trouble starts. And the trouble starts exactly at the point where everything I told you so far, I was cheating a bit. I was cheating because I'm studying processes where radiation is involved. And since radiation is involved and you don't have incoming radiation, you just outgoing radiation, the boundary conditions are not symmetric. You should use the in formalism. That consists, it's not that Galilei invented them, they applied them first to this system. So basically, when you derive your effective action, as in informalism, you have to first double your degree of freedom. Then you do your thing, that is, you integrate the action, you do your Feynman diagrams, and whenever you have a plus-minus propagator, it is a retarded propagator, and then you do your computation, and the object you obtain in the end is effective action in terms of a plus-minus variable, which I just a rewriting of the 1 and 2 variables. This object is not an observable per se, but you use it to derive equation of motion, the classical equation of motion, and you do it by deriving with respect to x minus and setting x minus to 0. That means identifying in the end of a process x1 and x2. So that is the way to do this when there are radiative mode involved. So how could you get along before and get the correct result? The point is that if by chance, not really by chance, but if the final product, the final action here, is of a form, a function of x1 minus a function of x2, you see it's exactly the same form here, then it means that even the final dynamics is conservative. And so you can just pretend nothing happened. You could, from the beginning, as long as you're interested in the conservative dynamic, just pretend nothing was going on and just do the thing that you do usually without doubling the degrees of freedom. That's why in the tail case, this thing worked even without using the informalism. But this is not always the case. And indeed, the memory thing is one of the points, as Blumen and others pointed out after our first mistaken derivation of a memory, you had to use the informalism. So let me just show you how the formalism work in concrete by stealing. I hope Raphael, who is listening, is not listening good because I stole it. I stole the equation from their paper where they derived the same quadrupole I derived before using the informalism. So this is the result. It's the same thing, you know, frequency domain, omega 2 is 6, it is I cube third derivative, etc., etc. And you will notice that, forget this for a moment, these terms here are of this form, which is exactly, if you go back to the other variables in time domain, it is a function of x1 minus the function of t1 minus the function of t2. No, sorry, a function of x1 minus the function of x2. So it is a conservative piece. That is exactly the piece we had obtained before. So in this case, that is completely, you know, things work in either way. The informalisms give you more than what you did before because they give you also the dissipative part, which is this one. In this case, the sine of omega and the imaginary part do not allow you to write the thing in this way. So this is a term which is purely dissipative, non-local term, and you take it away. And I mean, it is in the flux. Everybody knows that the tail has also dissipative part. In this case, also notice that you have a clear distinction between what is conservative and what is dissipative. This is conservative, this is dissipative. They are clearly distinct. In the memory and in the double emission term, well, this is not the case. So these are the diagrams I wrote them in Kelvin variables. This is the arrows telling you where propagators go, the target. And you have one family here and two families here. Blumlein, Meyer, Mercado-Scheffer computed this diagram. We recomputed them. We obtained the same result for this, and I think a different coefficient for this, but this is not the point. The point is that if you sum the two of these, you obtain an effective action in terms of a variable plus minus, which is not in the form of something 1 minus 2. Okay, these are the only two possible combination of Q derivatives modulo total derivatives which you can read, and the sum of these is not in this form. That means that this effective action is not conservative, purely conservative, and differently from above, from the tail case, you don't know where the dissipative part is precisely. It is ambiguous, which is the general situation when you have a neutral current which is not conserved. If a neutral current is not conserved, it's not defined unambiguously. You can always add a total derivative to it. And you don't know. There are situations in which you have something which guides you some approximated symmetry and something like that. In that case, you can identify the conserved current in some limit and then and fix the ambiguity. But this doesn't seem to be the case. We could try to do something. We could try to play the game further and just do what the informalism tells us to do. That is, you take effective action, you derive equation of motion, we obtain something which is the contribution to the acceleration of particle A given by these memory plus double emission terms. And I didn't bother to write the exact values of these coefficients, but given the Fourier expression, they're perfectly known. I could try to understand what the flux, what the dissipative part is by looking at the flux. So we just write the energy balance equation. So the derivative of the energy of the system must be given by this contribution, is given by this, where A is this object, you know, mechanical energy conservation. And I can write it as a flux due to these processes plus the generic short term, which is a total derivative of some function. You can just put it where you want. And this is the result for a flux plus short term for these two contributions which I showed you above, which is unhappily incompatible with the known result for the flux term of the memory, which is written here. I don't blush here, which is a result 2007, so pretty established. So what I mean with incompatible, it's more than what I need. I mean that there is no total derivative which you can add to this term to have this term. So they really don't go along together. And now there is a point where I disappoint everybody because I'm done. We are still working on it. So this is the situation in this moment. So I can just jump to the conclusions. So these terms, they are there. We must compute them. At 4 p.m. they are okay. At 5 p.m. we would like to have them. And the tail terms are, I would say, completely okay, completely understood. These memory and double emission terms are likely not yet. If I have to conclude on a positive note, if we get them, we get not only the 5 p.m., but probably the road is open to go 7 or even 6 or even 7 p.m. The reason is that the only other obstacle to go 6 p.m. is some integrals, some master integrals, which I frankly don't know whether they'll be computed or not. But once you know them, these integrals in the PN formalism, they have a property of being transporting by even. So if you know the solution at 6 p.m., you can go at 7 p.m. And so if we solve this little problem, we could really go really up with the PN computation, and that will be it.
Thank you for a nice and precise talk. Questions? Either on Zoom or in person?
This one's on? Okay. All right. So as a total outsider who has mildly dabbled in much lower orders, one thing that caught my eye was something about ambiguity in the conservative part on your slide. So as far as I've been able, you hear people talk about conserved and dissipative parts a lot. As far as I've seen, the definition of conservative is you use the time symmetric propagator instead of the retarded propagator. Okay, so you don't like that definition. So what is the definition, and then why is there any ambiguity?
I don't know, and there is just not a, for this phenomenon, there is not a conserved energy. If you have a system which doesn't have a symmetry, how do you define the conserved current?
Okay, maybe I misunderstood what you're claiming. Conservative part of what? Let's start with that.
A conservative part, I really mean an object for which this quantity is a total derivative.
Okay, if you're saying there's no conserved energy, that's okay with me.
Yeah.
Okay.
What we didn't appreciate before a couple of months, is that these objects is not purely conservative. It contains a dissipative part. And this dissipative part is not like in the tail case where you have a clear distinction. You can see what's conservative, what's not. Here it all comes together and
wait, so sorry. When do you ever see clearly what's conservative and what's not? That's the definition I'm looking for. What's the definition of conservative?
Well, I guess it depends on, consider a physical system or like the chiral symmetry. You know, you have a symmetry which is approximated. In that case, you can really take a limit and say, okay, in this limit, this symmetry is conserved. But here there is nothing like this, it seems. So I couldn't help more.
Well, I do have a question.
Yeah.
Yeah, so my understanding here is that you're not computing the full angle, right? you're comparing against the full angle would include some radiation.
Yes.
So are you certain that the origin of these discrepancies isn't just the fact that you're not computing,
It might be
the physical observable?
We are looking into it. I don't remember how much far, but yes, that's a possibility. Because normally the scattering angle, you just divide it into conserved derivative part and the dissipative part. And actually, beneath the Radico, they did some work to try to estimate the dissipative part of this. So there might be, but we're working on it. Clearly, there is, at this level, a problem in separating the two. There might be just that. That would be great, because then it shouldn't be a very difficult problem.
Yeah, so thanks for a nice talk. So yeah, I think maybe it's more like a comment maybe that I totally agree that yeah, once you have in this case the distinction between dissipation and conservative part is not well defined, because I can always subtract a conservative part and add to the original conservative part. However, I think a well-defined question is that if you hand me a conservative action, I should be able to check whether this is actually conservative or not by just checking whether energy and angular momentum are conserved.
Yes, but I don't have a conservative action to show you here, because this is the action. And if you derive a equation of motion of the action, you get something which do not allow for the conserved energy.
Right. Maybe another more like question now is, can you maybe comment on G2 the I think there's still debate about what's the conservative angle. Maybe you can comment on that.
I'm not sure. I'm not the most expert person to say about that. I read claims, but I'm not in a position to comment. I would like to understand more, actually. Yeah.
So this is a follow-up on Jason's question, but maybe rephrased in a different way. So those memory diagrams that you drew,
yeah.
Which order in G Newton are they? I think that answers that should be the answer.
Yes,
to the question.
yes. Okay, that is G squared, but then you have to use the equation of motion. It's so the question is it G4 or G5, right? I don't know, but I know the claim that at G4 there is no memory. It might well be, but at least there is a G5 component, that's for sure. So it might be the case that the G4 component is 0, but there is a G5 one.
So maybe to sharpen Sam's questions from a total non-expert outsider, why was it expected that what you were calculating here was the conservative part, thus leading to this surprise that there's potentially dissipative contributions? Is it because there's no external lines indicating emission, or why is it?
I just think we spent too much time computing the tails where this didn't happen, and probably we were biased. But no, think about it, 3 gravitational waves, 3 propagators here. But not so much, but this, you should expect some dissipative part, but we didn't realize it before.
Maybe I can ask if there's any questions on Zoom. I see there's a lot of experts too, so if you have anything to say.
Rafael is there.
Maybe I can just ask one question myself. So you started with some of your early slides where you pointed to this disagreement. I guess was being it a more prediction, and yeah. So you're saying this will be resolved by computing not the conservative Hamiltonian, but the complete Hamiltonian. Is that your claim?
That is what he was saying.
Okay, so you don't
But
have
maybe yes.
you don't have a
maybe.
suggestion how to cure
maybe,
this?
because this is just somehow conservative part of the scattering angle, and who knows whether even this distinction is correct at this level, because if there is an ambiguity here, there should be.
So it's not even clear that just
Yeah.
computing the whole Hamiltonian would
Exactly. Exactly.
fix it. Okay, thank you. Further questions? We have quite some time left. Yeah.
Yeah, so just you sort of say that you know, if we understand these issues, then the path to higher PN orders becomes somehow straightforward.
No, I wouldn't say straightforward, but
Well, I guess I'm asking, you know, couldn't there be other sort of, you know, creatures under the woodwork that can come crawling out?
This is a 4 PN diagrams. These are the 5 PN diagrams. If you just sit down and draw the 6 PN, they are all of this, they all this shape, and the rest cannot be worse than that. You can have an autopole here, but that's all. 7 PN is different. You have a tail of tail of tail. That's another thing. But I think there is some work on that by Michel Levy and collaborators on that. But 6 PN, just by power counting and drawing diagrams, you don't expect a priori, then you know surprises are always, but a priori don't expect any major problem from these kind of diagrams.
So I guess I'll follow up on my previous question. So physically, is it clear what interpretation we should have about these kinds of effects? Are they self fields that the binary is carrying with it? Does it correspond to actual radiation that reaches infinity and can be measured by an observer?
Well, this process has a corresponding process where radiation goes to infinity, for example, like this.
Yeah.
And if you compute the flux of gravitational wave emitted from these processes, that should correspond to the flux inferred by these closed diagrams. It's a kind of, no, sorry, by this one, yes. Kind of, it's not really the optical theorem, but kind of. But we have to work still on that.
So there's a corresponding radiative
Any closed diagram where there are gravitational waves involved, real gravitational waves,
yeah,
has a corresponding open diagram, and there is
right.
a relation between them.
But since these are closed diagrams that you're discussing here, should I think about them as like gravitational fields carried by the particles, some kind of self-energy, self-field?
No, this is a gravitational wave emitted. The binary emits 2 gravitational waves. They scatter, and they merge into one, which is the absorber.
Which returns to the binary. Yeah.
Maybe I will ask since we have time. So at order g to the 4th, one looks at the full angle. There's supposed to be effects that are quadratic in radiation reaction. Do you understand how these things show up in informalism? Or is it just when you compute the angle?
This diagram. This is a double emission vertex here.
Mm-hmm.
I think it should be that one. That is what my understanding of this.
But here you're computing the off-shell effective action, right?
Yes, but this is the process. Or if you want this one. That is my understanding of what this corresponds to.
I guess my confusion is that from that off-shell action, you would calculate some equations of motion that then you still use to compute the angle. And there seems to be effects that are quadratic when solving for the angle, which are not quadratic in the equation of motion.
Okay. I wish I had an answer for that, but we can talk that about later.
No questions assumed yet. Maybe this is your last chance to ask a question, either in Zoom or in person. We should probably then thank Stefano again.